We've already discussed some issues regarding losses in fusors. The deuterium-tritium reaction generates 17.6 mega-electron volts of energy. Given that it takes 150 kilo-electron volts to accelerate the deuterium ions, this means that if you just fired a stream of deuterium into a tritium target, then at least 1 in 117 particles would have to fuse to break even, assuming you had no losses in the system. However, we've also discovered that scattering is actually orders of magnitude more likely than fusion. Exactly how much depends on which energy we're operating at, but it's anywhere from tens to thousands of times more likely. So a particle is much more likely then to be deflected out of a target than to fuse with it. Obviously from this, for a machine to be successful, this scattered energy needs to be recovered in some way. In the Hertz machine, particles are recirculated through the target by the grid. Particles are accelerated into the target and then slowed down on their way out of the other side. Then, once they've slowed down, they're re-accelerated back through again. Although it is possible to retrieve energy from slowing particles using a grid, this is not implemented in the normal Hertz machine, and it is an inefficient process anyway, at less than 20% efficiency. Fortunately, there are ways of getting energy back from scattered charged particles, and these can be divided up into two techniques, a DC method and an AC one. Let's start by looking at the DC method. This technique is used in some high-powered valves, or electron tubes as they're known in the USA, like klystrons and gyrotrons. It consists of a number of catching electrodes at different potentials. As the particle passes through the fields generated by these electrodes, it is slowed down and is eventually caught by the electrode closest to its potential, where it flows back to ground, generating a current at that potential. This system has proved quite efficient when used with the valves mentioned earlier. The same idea could also be used for retrieving power from the charged fusion products. One way of implementing this is with concentric grids in the machine at different potentials as shown in the diagram. The second way of retrieving energy might be called the AC method. In this case, we pulse a particle source at a known frequency and retrieve the energy using tuned electromagnetic cavities as shown. And in fact, both these methods could be combined together. However, mopping up scattered particles alone is not the end of the matter. If the scattered particles impart some of their energy to low-level movement in a target, this is effectively low-grade lost heat. Some studies have been done which indicate that this is an issue. And as with all machines, the second law of thermodynamics must be satisfied. The other issue is low-speed target particles being bumped out of the trap in the middle of a machine, but not being energetic enough to be effectively dealt with by the energy retrieval apparatus just described. Again, you might think of this as a low-level heat loss also. Some of these low-level losses will be retrievable by careful design of the energy collectors, but others will have to be reduced simply by good design of a machine.